Okay, good morning everyone. Just to recap the lecture yesterday quickly, we had a look at a two-body problem which we, by using symmetries, were able to reduce to an effective one-body problem, which simplifies the treatment a lot because we started out with 6 degrees of freedom, and by using first a translational symmetry and exploiting that the Lagrangian was independent on the center of mass coordinate, we could reduce the problem to an effective one-dimensional one. And further, we also made use of an additional symmetry, namely rotational symmetry, due to the fact that we have a central force field. And by that we were able to identify the movement of the particle, namely that it had to be confined to a plane. So that was briefly the content of what we did yesterday, and we ended by deriving the equations of motion. Now, since the movement was confined to a plane, it sufficed for us to consider two generalized coordinates, namely r and theta. And we show that due to the conservation of angular momentum, because of the rotational symmetry, there was a conservation law associated with L, the magnitude of the angular momentum. And this could be used to eliminate the time derivative of the angle. So what we ended up with was this equation. This is Lagrange equations for r in the problem. And then we eliminated this coordinate to obtain this equation, which is now manifestly one-dimensional. There's only dependence on the radius here. So we see that the acceleration, the radial acceleration, is given by an effective force, F prime, which is equal to the external force, the original force acting on the system, the object, the particle, plus this additional term, which stems from the conservation of angular momentum. Now, the very last thing we did in the lecture yesterday was to identify what this term actually is, or at least I suggested what it should be. Because it's given like this, which may be written as mv theta squared over r, where v theta is the linear velocity, given by the angular velocity multiplied with the radius. Does this look familiar to you? Where have you seen it before?
Centripetal acceleration.
Absolutely. It's a centripetal force. And the centripetal force is, you can think of it as the force required to keep a particle in circular motion. If you want to have a particle that is orbiting some point, you need to have a centripetal force to keep it in this motion, or else it's just gonna escape tangentially. So it has the magnitude, at least, of the centripetal force, but what about its direction? We see here that m multiplied with the radial acceleration is equal to the external force plus this term. So it's acting outwards. It's acting in the direction of the radius. Whereas the centripetal force is the force required to keep the particle in orbit, so it has to be applied inwards towards the center. So this is in fact the centrifugal force. The centrifugal force is a term which appears in different contexts and it has slightly different meaning depending on which context it appears in. For instance, you may be accustomed to thinking of the centrifugal force as something fictional, that is not a real force, it's something that appears in accelerated systems. And in a specific context, this may be the case. For instance, if you have let's say you have a car driving around some rhododendron or something, then a person inside the car will feel as if he's pulled towards the outer edge of the car. This is a centrifugal force, but there's no actual force being applied to him. It's just something that he experiences. So in this sense, you can think of it as a fictional force. But in this case, we have a particle which is orbiting possibly some point due to the fact that it has an angular momentum. So if L is non-zero, it means it has some kind of rotational motion around the point. And if we look at this term, then consider some fixed value of L. So let's say we have an object which has a fixed angular momentum. We then see that what happens when you approach the center of the orbit, as r goes to 0, in other words, this term diverges, becomes very large. And it basically means that it's harder to keep an object moving rapidly close to to the center of the orbit as opposed to moving in a larger radius. You would need a larger force to keep it there. So basically, we need some external force, F, in order to balance this centrifugal force if we want to have some particle orbiting. Did the sound just vanish? Oh. Let me just get rid of this one. So we need to have some external force which balances this centrifugal force if we aim to have a stable motion of the particle around some center. So the centrifugal force here is acting outwards. Equivalent to this description, where we have sort of a Newton's second law for the radial motion with the external force and this additional centrifugal force, we could alternatively consider the energy equation. Which looks like this. So we see that the conservation of energy can be written as a kinetic part plus an effective potential energy, V prime here, consisting of the original potential energy or the external potential energy and this additional term due to the conservation of angular momentum. So we have an effective potential which gives this effective force. And since we have a conservative system, the relation between f prime and v prime is given in the usual way. All right, so we haven't specified the potential energy so far, but it's clear from these equations that the motion of the particle, the orbit it will take, depends on the precise form of the potential energy, in particular how it's balanced compared to the centrifugal force. So what we'll do is we'll have a look at a specific example for V of r and see what kind of motion can we obtain. The example we'll consider is an attractive force which goes as 1 over r squared. And we're considering an attractive one because otherwise the resulting motion would be pretty trivial. Then you would have two repulsive forces and the particle would just escape. Okay, so the force is written like this, where K is some constant characterizing the strength of the force and also giving it its proper dimension. So with this force, this relation here implies that the potential has to be given like this, minus K over R. So the effective potential that the particle feels is given like this. The sum of this attractive potential and the centrifugal barrier, if you like. Because you can think of this potential as a barrier. And let's see why that is the case. So let's have a look at this V prime of R, what it actually should look like as a function of distance. Well, we can start with this term, minus K over R, which should look something like this. As R goes to 0, it should diverge along the minus side of the axis. And as R goes to infinity, it should approach 0. So something like this. This term, on the other hand, behaves qualitatively in the same way, but just with the opposite sign. However, note that there's an R squared here, which means that it actually diverges faster as you approach 0. So this is minus K over R. This is the centrifugal barrier. And we can now understand why it's appropriate to name it a barrier. Because it diverges here, so it creates an energy barrier for the particle to overcome if it is supposed to be located close to the center. And this is from a classical physics point of view, because in classical physics, in order for a particle to be located in some area which has a potential energy, the energy of the particle has to be larger than the potential energy, or at least as large as the potential energy. In quantum mechanics, this can change. You can have, for instance, tunneling phenomena, where the particle tunnels through a barrier even though it has insufficient energy. But this is a different story. So we need to have such a condition. Okay, but the total potential is now the sum of these two. So we have to consider what that would look like. And this full drawn line is V prime. And how come we can conclude that it has this form? Well, we stated that this term would actually diverge faster as we approach 0 compared to this one. So as we go towards r equals 0, V prime should be dominated by this term. However, as r goes towards infinity, this term here goes to 0 slower than this term, since we have r squared. And this means that as r becomes large, this term, minus k over r, should dominate. So in the limits 0 and infinity, we should have V prime getting close to this curve here, whereas it should become close to this curve here. And effectively, there has to be some point along the way where we have a minimum, where this curve changes from being close to that term to this term here. So it should look qualitatively something like this. So let's just write down these limits. And I just put a minus here to indicate that V prime approaches 0 from below, from a negative value. Okay, so we have identified what V prime looks like, more or less. Should have qualitatively this form. And what I would like to discuss now is that depending on the energy of the particle, we will have different types of qualitative motions. So let's consider first the case where the energy of the particle is E1. E1 is larger than 0. And keep in mind that the energy of the particle should always be greater than or equal to the minimum point of the potential energy, because the energy is given as the potential energy plus the kinetic energy. So the kinetic energy ensures that we will always have this, at least at some point, along the potential energy. Okay. So if this is the case, we have a particle with positive energy, and the magnitude of the energy is, say, there. Please take 1 minute to discuss with your neighbor what kind of motion would you expect for this particle. All right, do you have any ideas? Any suggestion? Yep.
Particle would just escape from towards large R.
Mm. And how do you reason to conclude with that?
Qualitatively, it's the potential is 0 at large R, and it's larger at small r.
Mm.
Therefore, it would go towards large R.
Yeah. Exactly. So, just as to say, the energy here is much larger than potential at large R, whereas it's actually bound here. The particle cannot, in fact, get any closer than this R. If you call this R1, because the closest distance the particle can arrive at has to be the position where the energy is equal to the potential energy. Because it's, in classical physics, forbidden for a particle to be located at a position where the potential is larger than the energy. So it can't get to 0, because there the potential energy would be greater than the energy. So basically, the particle cannot get any closer than R1 due to this potential barrier. However, there is no upper limit for R. The particle is completely free to move here because the energy is greater than the potential energy. So if we were to consider the resulting orbit or trajectory of this particle, we would have to have some kind of trajectory which would have a minimum distance, but also should be unbound, because it can approach large R without any obstacle. So if this is the center of our coordinate system, and we have a particle incoming from here, something like this should capture qualitatively the motion of the particle. It approaches the center and then cannot get any closer than R1 before it escapes and just continues. So something like this. And if we do the analysis more rigorous, in fact solve for R as a function of time, as we will do later, this would actually turn out to be a hyperbole, this trajectory. Now, let's consider a scenario where the energy of the particle is now E2. And let's consider the case where E2 goes to 0. So the particle has actually 0 energy. how would you expect this qualitative sketch of the trajectory to change? Any ideas? Well, if we follow the same line of reasoning as we did for E1, we saw that E1 was bounded from below, could only get as close as R1, but there was no upper limit. Yep?
Well, I'm just going to guess that if you approach it from above, you'll have an unbound trajectory, but if you come from below, you'll have an exactly bound, maybe?
Okay. So how do you mean when you say approach from above and below?
You know, you say that the energy approaches zero, but say
I see.
it approaches zero from above or below.
Yeah, that's a good point. Okay, let's attach a plus here. Yeah. So you're right. If the energy is, well, in fact, if the energy is exactly equal to zero, the motion would still be unbound for large r, because this potential goes towards zero as r goes to infinity, but it never becomes exactly zero.
Yeah.
So in either case, as long as we consider exactly zero energy, we would have actually the same type of motion. We have a minimum distance, r2 in this case, which is larger than r1, but we still have unbound motion in this direction. So we get qualitatively the same type of motion. Now, what happens if we consider energies with that are below zero? Is that even possible? Can a particle have less than zero energy? Is that a nonsensical statement? Yep.
Well, it works because you define that the potential energy is negative.
Yes.
So it just means less kinetic than potential energy. It will be in some orbit.
Exactly. So it's actually possible to have a negative energy depending on how you define or where you define the reference level for potential energy. And just as you suggested, when you see a negative energy, this is often closely related to a bound state or a bound orbit. So let's see why this is the case. Here's our potential energy. And we consider some energy of the particle, E3, which is now negative. So please take 30 seconds just to think. Following the same line of reasoning that we did over there, what kind of orbit would you expect in this case? All right, any ideas? Yes?
Well, you'll get an elliptic or a circular orbit. That's what the question is.
Okay, so how do you reason to?
Well, if it's bound in some kind of routine trajectory, those are your options. And I'm guessing the circle has the lowest energy because you need less energy to keep it in a circular orbit than in an elliptic.
Possibly, I'm not 100% sure about that statement.
That's what I remember from space.
Okay, that could be a case, I just can't see it immediately. But as you say, it should be some bound orbits and examples of bound orbits, although they're not the only possible bound orbits, are ellipses and circles. But we could have other types as well. So the question is then, okay, do we have a circular or elliptical orbit in this case, for instance? Or do we have neither? Well, if you follow the same line of reasoning as over here, we see now that there are two radiuses here, which the particle cannot exceed, because it can only be in a regime, classically, where the energy is larger than the potential energy. So the particle has to be confined to this shaded area. It cannot rise above it. So we see that it's confined now to a motion between R1 and R2, which are different. So the particle has to be located at a radius which is between R1 and R2. But this does not necessarily mean that the orbit has to be elliptical. In general, we can have an arbitrary type of motion. It depends on the exact choice of the potential energy. But we know that one thing we do know is that the particle can only move inside this regime, inside this donut, if you will, defined by R1 and R2. Now, I just drew this trajectory as an example, and the actual trajectory that the particle has to follow doesn't necessarily have to be closed like this. But this is just to illustrate the motion. I have one final case, which, yes, sorry.
Okay, I'm just, if you have the energy at the perfect bottom of the VR graph, you see that both the R's be the exact same, and so that will be the circular graph.
That would be the circular. So that was actually the final case I wanted to consider is when E4 is actually at the bottom, as you say. When the energy of the particle is equal to the minimum of the potential energy. In that case, as you point out, the radiuses R1 and R2 are actually the same. And we can call that R0. If the radius is constant, the time derivative has to be 0. Now we know that this condition has to be satisfied at the minimum of the potential energy. And it would then follow that the associated force has to be 0. And if we recall our expression for f prime, what it consists of, we know that it consists of the external force, any external force F in the system, plus this term originating from the conservation of angular momentum. So F prime equals 0 implies that F has to equal minus mr theta dot squared. Is this a reasonable result? If we try to think physically, what does this equation mean now? So keep in mind that this term we interpreted as the centrifugal force. Well, this equation expresses that if the external force F is equal in magnitude but opposite in direction due to this minus sign as the centrifugal force, the motion of the particle will be a circle. And we know that the magnitude of the centrifugal force is 1/2 mv theta squared over r, the magnitude of the centripetal force required to keep the particle in a circular motion. So this makes sense. When the external force balances the centripetal force required to keep a particle in circular motion, we get a circular orbit. So IE here means in effect. I think we'll take a break there.